In this lesson, we will discuss how to work with array and waveform data types, and how to work with single-channel and multi-channel acquisition data. In this section, we will learn about the array data type and waveform data type. The array data type is a collection of data elements of the same data type. For example, this array is a collection of numerics, this array is a collection of booleans, and this array is a collection of strings. Here, we see an example of an array. Each item in the array is called an array element. This example array consists of 10 array elements. Each array element has a corresponding index number that specifies the array element's location within the array. The first array element has an index of 0. The second array element has an index of 1. The third array element has an index of 2, and so on. The array element at index 6 has a value of 27, and the array element at index 9 has a value of 30. Arrays can have one or more dimensions, for example, length, height, or depth. On the left, we see a one-dimensional array, which extends in only one direction. On the right, we see a two-dimensional array, which extends in two directions, so we have rows and columns. This 2D array shows its array elements in a grid of rows and columns. A 2D array has both a row index and a column index, both of which start at 0. I can specify a specific array element using the row index and column index. For example, this array element is at row index 0, column index 6. I can also specify an entire row using the row index. For example, this is the row at row index 2. Similarly, I can specify an entire column by saying this is the column at column index 8. You can view numeric array data as an array indicator or as a graph. These two indicators show the same data. The array indicator lists the data points. This graph indicator shows that same array data as a plot. Notice that the y-axis represents the array values, and the x-axis represents the array index. Each point represents one array element, and the plot connects the points with lines. This is an example of how a 2D array is visualized by an array indicator and a graph. The graph interprets each row of the 2D array as a separate plot. An uninitialized array has a defined number of dimensions and a defined data type, but contains no data in its elements. The uninitialized array in this example has 2 dimensions and has a numeric data type, but it contains no actual data. An initialized array has a defined number of dimensions and data type, and also contains data in its elements. The initialized array in this example has 2 dimensions with 2 rows and 3 columns of defined numeric data. To create an array, I'll add an unconfigured array to the panel, and then rename it. Next, I'll define the data type of the array. To make a numeric array control, I will place a numeric control inside the unconfigured array. To resize the array to show 6 elements, I can click and drag either of these blue dots. Because this is a 1D array, I can only resize the array in one direction. Notice that the 6 elements appear grayed out. This is because these elements are uninitialized and contain no actual data. Now, I'll enter data into the array control. This is the array index display, which controls which array element is shown at the leftmost element. Right now, the element at index 0 is shown here. Now the element at index 1 is shown here. Notice how the array index display affects which elements the array control shows. Now, I'll wire this array control to a graph indicator. And then run the VI. Notice how the 1D array data is visualized in the graph indicator. I can click the plot legend and configure the visual style of the plot. I can also rename the axes on my graph. As you can see, here's the array data point at index 0, and the array data point at index 1, and so on. To create a two-dimensional or 2D array, you must change the number of dimensions from 1 to 2. You can do this in the Item tab here. Now I can resize the 2D array to show a grid of rows and columns. Now I'll enter data into my new rows. Notice that the index display now shows two numerics. The top numeric refers to the row index. The bottom numeric refers to the column index. Now I'll run the VI. Notice that each row in the 2D array represents a separate plot in the graph indicator. Click each plot in the plot legend to configure it. You can configure the appearance of an array control in the Item tab in the Layout section. You can configure whether to show the index display, horizontal scroll bar, and vertical scroll bar. The waveform data type is made up of three items. T0 specifies the start time of the waveform. dt specifies the time interval in seconds between data points in the waveform. The y numeric array specifies the data values of the waveform. You can visualize the waveform data type using a waveform indicator, or graph. As you can see, the y array data values represent the data values of each point in the waveform. The T0 initial time item and dt interval time item in the waveform data type provide timing information. Because of this, the x-axis for a graph with a waveform data type can be in units of time. The dt, or interval time, specifies the time interval in seconds between data points in the waveform, as shown in the graph. The T0 initial time specifies the start time of the first data point in the waveform. If you need to extract the individual y array, T0, or dt waveform items, then use the Waveform Properties node to access the specific item. Let's examine the waveform data type. In this VI, the waveform control passes its data directly to the graph indicator. If I run the VI, you can see the data values in the waveform control are shown as points in the graph, and the dt item determines the time interval between data points. Notice how changing the dt here changes the time interval between points on the graph. Notice that the x-axis is in units of time, in seconds. If we want to see the x-axis with time and date information, you can select the x-axis, and then change the display format to absolute time. Notice that the first point on the x-axis matches the T0 initial time in the waveform control, and the last point on the x-axis is 1 second later. Now, I'll change the display format back to showing time in units of seconds. Now, let's examine a 1D array of waveforms. Notice that this 1D array contains 3 waveform elements. All 3 waveform elements contain the same T0 initial time and dt interval time. The 1D array waveform passes its data directly to the graph indicator. Now, I'll run the VI. The graph displays each waveform in the array as a separate plot. Let's see what happens if I change the dt interval time of one of the waveforms and run the VI. Now, let's see what happens if I change the T0 of one of the waveforms to 1 second later and run the VI. In this section, we will learn how to work with single-channel acquisition data. If you are acquiring one channel, one sample data, it will typically be returned as a DBL numeric data type. If you are acquiring one channel, n sample, in other words multiple sample data, it will typically be returned as either a 1D DBL array data type or a waveform data type. This VI acquires and displays one channel, n sample data as a waveform data type. Notice that the DAC-MX read is configured for single channel, multiple samples, and waveform data format. I can visualize this data as a regular waveform indicator or in a chart indicator, which shows a history of data written to the chart in previous loop iterations. To configure how much historical data a chart can show, click the chart and change the history length, and adjust how many points the x-axis shows. I can also visualize this data in a graph indicator, which only shows the multiple samples for the current loop iteration. Now, let's run this VI. The waveform indicator shows the one channel and sample data for the current iteration. The chart indicator shows historical data, the most recent 5,000 samples, in this case 5 seconds of data. The graph only shows the 1,000 samples from the current loop iteration, in this case 1 second of data. This VI acquires and displays one channel and sample data as a 1D DBL array data type. Notice that the DAC-MX read is configured for single channel, multiple samples, and floating point data format. I can visualize this data as a 1D DBL indicator or in a chart indicator, which shows a history of data written to the chart in previous loop iterations. To configure how much historical data a chart can show, click the chart and change the history length, and adjust how many points the x-axis shows. I can also visualize this data in a graph indicator, which only shows the multiple samples for the current loop iteration. Now, let's run this VI. The 1D DBL indicator shows the one channel and sample data for the current iteration. The chart indicator shows historical data, the most recent 5,000 samples. The graph only shows the 1,000 samples from the current loop iteration. Graphs and charts include tools to help you zoom in on data, add cursors, and change plot styles. To zoom and pan data on a graph or chart, go to the Item tab and enable the Graph tools. Click this button to zoom. I'm going to choose to zoom horizontally, and click and drag the area to zoom. Click this button to pan. I'm going to choose to pan horizontally. Click this button to zoom to fit all data on the graph. To add cursors, go to the Item tab and enable the Cursor legend. Then click the Add Cursor button, and you can give it a descriptive name. Click the cursor to configure it in the Item tab. You can choose to display the name and value, choose the cursor color, cursor target shape, and whether to fill the shape. You can also configure which plot you want the cursor to snap to if you have multiple plots. As I move my cursor, notice that the X and Y coordinate values update in the legend. I can click the cursor legend header to change the column names. I can also add multiple cursors. I can configure the appearance of the X and Y axes by clicking on the axis name and going to the Item tab. Notice that I can configure the display format, label and grid visibility, axis position, tick marks, autoscale settings, and more for each axis. To configure the appearance of a plot, click on the plot in the plot legend and configure its style. Next, we will look how to process one channel and sample data when it is represented as a waveform data type. In this example, the DAC-MX read is returning a waveform data type that represents one channel and sample data. Let's look at how the math nodes work with the waveform data type. If you use a math node, such as an add node, to add a waveform and scalar, like a single numeric, the add node will add the scalar value to every single data point in the waveform. As you can see here, the original waveform contained a sine signal. So when you add a scalar 3 to the waveform, the result is the entire waveform is offset by a value of 3. If you use a math node, such as an add node, to add a waveform with another waveform, the add node will add each corresponding point from each waveform together. As you can see here, when you add a sine waveform with a noise waveform, the result is a noisy sine waveform. When performing a math operation on two waveforms, make sure that both waveforms have the same dt, that is interval time, and the same number of data points, that is y array length. Next, let's talk about the workflow for using the analysis nodes. First, I will capture some acquisition data. Second, I will configure an analysis panel to analyze the captured data. Third, I will copy the configured analysis onto my diagram as an analysis node. So I'll start by running this VI, which acquires data as a waveform data type and displays it in this graph. I'll stop the VI, and now I'll capture the data from this graph. Next, I'll open the captured data item. And now I'll launch the Filter Analysis panel. I'll adjust this analysis panel's configuration settings until I get the desired result from my application. Next, I can click and expand the configured code section of my analysis panel and click Copy to Clipboard. And now I'll go to my diagram and press Ctrl-V to paste an analysis node with the corresponding configuration settings. Now, I'll create a new indicator for my filtered signal. And run the VI. Now I can see my original acquired signal and my new filtered signal. If I ever want to adjust the settings of my analysis node, I can edit these constants, or I can also click the Analysis panel button here, make adjustments in the Analysis panel, and click the Update node here. And my analysis node code has been updated. Next, we will learn how to process one channel and sample data when it is represented as a 1D DBL array data type. In this example, the DAC-MX read is returning a 1D DBL array data type that represents one channel and sample data. Let's look at how the math nodes work with the 1D DBL array data type. If you use a math node, such as an add node, to add a 1D DBL array and a scalar, the add node will add the scalar value to every single data point in the 1D DBL array. As you can see here, the original waveform contained a sine signal, so when you add a scalar 3 to the 1D DBL array, the result is the entire waveform is offset by a value of 3. If you use an add node to add a 1D DBL array with another 1D DBL array, the add node will add each element pair together. But it will only do this until the last element in the shorter array. Notice in the second example, the top array has 3 elements and the bottom has 4 elements. So the array result only contains 3 elements. Now, let's talk about the analysis nodes with the one-channel and sample data. Some analysis nodes only work with the waveform data type and will not work with the 1D DBL array data type. Some analysis nodes work the same, whether the data type is a waveform or 1D DBL array. For example, the statistics analysis node returns the same data whether the signal input is a waveform data type or 1D DBL array data type. Some analysis nodes require an additional timing input if the signal input is a 1D DBL array data type. This is because the 1D DBL array data type only contains data values, but does not contain any timing information. For example, the FFT spectrum analysis node requires timing information. If the signal input is a waveform data type, the waveform already contains the DT timing information. However, if the signal input is a 1D DBL array data type, then the FFT spectrum analysis node adds a DT input so you can provide the DT information to the node separately. As another example, the filter analysis node also requires timing information. If the signal input is a waveform data type, the waveform already contains the DT timing information, so the filter analysis node can calculate the sampling frequency of the signal. However, if the signal input is a 1D DBL array data type, then the filter analysis node adds a sampling frequency input so you can provide that timing information to the node separately. In this example VI diagram, the filter analysis node receives 1D DBL array data from the DACMX read node. This VI also provides the sampling frequency from the DACMX task properties node to the filter analysis node. In this section, we will learn how to work with multiple channel acquisition data. If you are acquiring N-channel one-sample data, it will be returned as a 1D DBL array data type, where each element represents one sample from each channel. If you are acquiring N-channel N-sample data, it will be returned either as a 2D DBL array data type or a 1D waveform array data type. For the 2D DBL array data type, each row represents multiple samples from one channel. For the 1D waveform array data type, each waveform element represents multiple samples from one channel. This VI acquires and displays N-channel one-sample data as a 1D DBL array. Notice that the DACMX read is configured for multiple channels, single sample, and floating point data format. I can visualize this data as a regular 1D DBL array indicator, or as a chart indicator, which shows a history of data written to the chart in previous loop iterations. For this N-channel one-sample 1D DBL array to show up correctly as separate plots in the chart, you must add an array to cluster node between the array and the chart. Now, let's run this VI. The 1D DBL array indicator shows the N-channel one-sample data for the current iteration. The chart indicator shows historical data and a separate plot for each channel. This VI acquires and displays N-channel N-sample data as a 1D waveform array. Notice that the DACMX read is configured for multiple channels, multiple samples, and waveform data format. I can visualize this data as a regular 1D waveform array indicator or in a chart indicator, which shows a history of data written to the chart in previous loop iterations. To configure how much historical data a chart can show per plot, click the chart and change the history length, and adjust how many points the x-axis shows. I can also visualize this data in a graph indicator, which only shows the multiple samples for the current loop iteration. To configure the DACMX channel control to specify multiple channels, I can use the AI0:3 syntax to select channels AI0, 1, 2, and 3. Now, let's run this VI. The 1D waveform array indicator shows the N-channel N-sample data for the current iteration. The chart indicator shows historical data, the most recent 5,000 samples per channel, and a separate plot for each channel. The graph only shows the 1,000 samples per channel for the current loop iteration, and a separate plot for each channel. This VI acquires and displays Nchannel and sample data as a 2D DBL array. Notice that the DAC-MX read is configured for multiple channels, multiple samples, and floating point data format. I can visualize this data as a regular 2D DBL array indicator or in a chart indicator, which shows the history of data written to the chart in previous loop iterations. To configure how much historical data a chart can show per plot, click the chart and change the history length, and adjust how many points the x-axis shows. I can also visualize this data in a graph indicator, which only shows the multiple samples for the current loop iteration. For this Nchannel nsample 2D DBL array to show up correctly as separate plots in the chart, you must add a transposed 2D array node between the array and the chart. To configure the DAC-MX channel control to specify multiple channels, I can use the AI0:3 syntax to select channels AI0, 1, 2, and 3. Now, let's run this VI. The 2D DBL array indicator shows the Nchannel nsample data for the current iteration, and each row represents a separate channel's data. The chart indicator shows historical data, the most recent 5,000 samples per channel, and a separate plot for each channel. The graph only shows the 1,000 samples per channel for the current loop iteration, and a separate plot for each channel. Because Nchannel data is represented by a 1D waveform or 2D DBL array data type, you can manipulate the data using the array nodes. LabVIEW NXG groups the nodes you can use to manipulate arrays on the array palette. Let's discuss some of the common array nodes. The array size node returns the number of elements in the array. For example, if you have a one-dimensional array of temperature data and need to know how many samples of data are in the array, you wire the temperature array to the array size node. When you run this VI, the indicator shows 10. There are 10 elements in the array. For a multi-dimensional array of temperature values, the array size node outputs the size of each dimension. In this example, the 2D temperature array will output an array size of 2 dimensions. The first element equals 2 for 2 rows, and the second element equals 10 for 10 columns. The array subset node returns a portion of an array starting at an index you define, and it contains the number of elements you define as the length. In the temperature data example, let's say you want to use the data for the 4th and 5th elements. Remember that arrays are always 0 indexed, so you wire the index value of 3, which is the 4th element in the array. Then you enter the length as 2, which will include the 4th and 5th elements. The result is that we get a subarray of 2 elements. The build array node concatenates elements together into one array, or concatenates multiple arrays together into arrays of higher dimension. Let's say you need to add more measurements to a single channel in the temperature array data. You can wire a single scalar element into the build array node, and it automatically concatenates the new measurement to the temperature array. The build array node is a resizable node. It can be resized to add additional input terminals. If you want to add another channel of temperature measurements to the 1D array, you disable Concatenate Inputs in the Item tab. Then, when you create a 2D array, each channel is a separate dimension. The index array node returns the element or subarray from an array at an index that you define. In the temperature example, you can use the index array node to extract an element at a particular index. For example, if you wire the constant 6 to the index input, you get the element at that index position. Similarly, we can extract entire rows or columns in multi-dimensional arrays. When you wire an array to this node, the node resizes automatically to display index inputs for each dimension in the array. In this example, the DACMX read node returns Nchannel nsample data as a 1D waveform data type. We can extract one channel's data by using the index array node. The index input specifies which channel to extract. When working with an n-channel array, a common task is to run the same processing algorithm on every channel of the n-channel data. To do this, we can use a for loop with auto-indexing tunnels. For loops and while loops can configure an input tunnel to iterate through an array's elements, and configure an output tunnel to build an array. This is known as auto-indexing. While working on an array, you might want to access every element of the array individually. You can use a for loop with an auto-indexing input tunnel to process one element of an array during each iteration of the loop. There is no need to wire the end terminal of the for loop. The for loop will execute the exact number of iterations necessary to iterate through each element of the array. This example has a 5-element array wired to the auto-indexing input tunnel, so the for loop will execute 5 iterations, with each iteration extracting the next element in the array. A for loop with an auto-indexing input tunnel behaves similarly to a for each loop in other programming languages. To configure the behavior of an input tunnel of a loop, select the input tunnel, and then in the Item tab, enable auto-index values. If the end input is wired and multiple arrays of different sizes are wired to the auto-index tunnels, the for loop uses the smallest of the choices to determine the number of loop iterations. For example, this VI has an end input of 10, a 15-element array, and a 5-element array. So the for loop chooses the smallest of these, which is 5, and executes only 5 loop iterations. The final iteration indicator shows 4 because the iteration terminal starts counting at 0. If you want to collect the result of each loop iteration in an array, use an auto-indexing output tunnel to pass an array of those values out of the loop. If you want an output tunnel to return only the value from the last loop iteration, use a keep last value output tunnel instead. To configure the behavior of an output tunnel on a loop, select the output tunnel, and then in the Item tab, configure its append mode. Additionally, you can determine which values to write to an auto-indexing output tunnel based on a condition. To do this, select the auto-indexing output tunnel, and in the Items tab, enable conditional output. Now, the auto-indexing output tunnel will only store a value if the conditional input is true. In this example, only values that are less than 5 will be written to the auto-indexing output tunnel. Now that you know how to use for loops with auto-indexing tunnels, you can use this technique to iterate through each channel in an Nchannel data array, process each channel, and output the process results of each channel to another array. This example acquires Nchannel nsample data as a 1D waveform array data type. It displays the acquired data in this graph. The multiply node is able to accept this data type and scales all the channels and outputs them to a scaled channels graph. The filter node is also able to accept this data type and outputs the filtered data to a filtered channels graph. The RMS node does not accept the 1D waveform array data type, so we can process every channel in the 1D waveform array by using a for loop with an auto-indexing input tunnel and an auto-indexing output tunnel. This outputs the RMS values for all channels to the RMS values 1D array indicator. The DAC-MX channel control is set to acquire channels AI0, 1, 2, and 3. Now let's run this VI and see the results. Here's the acquired data for all 4 channels. Here's the scaled data, which has been multiplied by 100 for every channel. Here's the filtered data for every channel. And here are the RMS values for every channel. In this section, we will explore some additional real-world examples that use arrays. This example implements generating a voltage ramp on an analog output channel. First, let's examine the VI's behavior. Here's where I can set the analog output channel and my voltage ramp settings. In this example, I want a linear ramp of 11 voltages, starting from 0 volts and ending at 5 volts. I also want this VI to output each voltage for 1 second. Now, let's run the VI. Notice that these 3 ramp configuration values have generated this ramp pattern. And this indicator displays the current analog output channel output, which shows the VI executing the values in the ramp pattern one after another. Now, let's examine the diagram. We can use the ramp pattern node to programmatically generate a 1D DBL array that contains our ramp values. Then, we can wire this array to an auto-indexing input tunnel, and the for loop will write each ramp value to the analog output channel. We can use this control and the wait node to set how many milliseconds we want the voltage ramp to stay at each ramp value. Lastly, we can use a DAC-MX write node before the loop to set an initial analog output voltage value, and a DAC-MX write node after the loop to set a shutdown analog output voltage value. This example outputs stimulus values on an analog output channel, waits for a defined settling time, and then acquires the corresponding response values on an analog input channel. First, let's examine the VI's behavior. Here is where I can set the analog output channel, settling time, analog input channel, and stimulus values. Here is where I can view the current stimulus and response values. And here is where I can view all the response values at the end. Now, let's run the VI. Notice that the VI is setting stimulus values one after another and acquiring the corresponding response value. When the VI is finished, we can see all the acquired responses. Now, let's examine the diagram. Here's the code for the analog output channel, and here's the code for the analog input channel. This is the array containing all the stimulus values, which is wired to an auto-indexing input tunnel. The for loop will read the stimulus values one at a time. For each for loop iteration, it will get the next stimulus value and write it to the analog output channel, then wait for the specified settling time, read the response value, and then write the response value into the auto-indexing output tunnel. After the for loop completes, the output tunnel will output all the response values to an array indicator. If you need to generate a waveform signal on an analog output channel, you can use a 1D dBl array. This example VI generates a user-defined sine wave on a DAC-MX analog output channel. The sine wave node here is configured to create a 1D dBl array of sine wave data points, and it sends it to the DAC-MX write node, which stores these data points in a hardware buffer on the DAC device. Also, the sample rate is sent to the DAC-MX timing node, which sets the rate at which the DAC-MX device will output the analog output channel's voltage. For example, if the sample rate is 10 Hz, the DAC-MX device will update the analog output channel every 0.1 seconds with the next data point. When the DAC-MX start executes, the DAC-MX device will output the data points specified by the 1D dBl array at the specified sample rate. The VI will then go to the DAC-MX wait until done node and wait until the DAC-MX device has finished outputting all the data points. If you need to generate a waveform signal on an analog output channel, you can also use a waveform data type. This example generates a user-defined sine wave on a DAC-MX analog output channel. The sine wave node here is configured to create a waveform data type of sine wave data points, and sends it to the DAC-MX write node, which stores these data points in a hardware buffer on the DAC device. The DAC-MX timing node here is configured to use waveform timing, so we can wire the waveform into the waveform input. This causes the DAC-MX timing node to use the input waveform's dt to determine the rate at which the DAC-MX device will update the analog output channel's voltage. You can use two for loops to programmatically create a two-dimensional array. The inner for loop creates an array with 6 elements. The outer for loop takes the output of the inner for loop, the array with 6 elements, and places it as a row in a two-dimensional array. So the end input of the outer for loop determines the number of rows in the 2D array, and the end input of the inner for loop determines the number of columns in the 2D array. You've completed this module. Here is a summary of what you've learned.